problem in the previous classes. So this is how the stiffness matrix for a plane truss, space truss problem look like. Okay, that is in the local coordinate system. Then also we had the transformation matrix. So if the member was not a vertical member, that is the definition of vertical is it should be parallel to y-axis, global y-axis. So if it's not a vertical member, then basically we did these two transformations. We rotated the global x-axis about global, we rotated the global coordinate system about the global y-axis as shown here, okay, by an angle beta, okay, in such a way so that my x beta or xs after rotation by beta, that's what is called x beta is right under xm, vertically below xm. Then we rotate the global coordinate system again with respect to z beta, okay, by an angle gamma until my x is aligned with xm. Okay, for a space truss, we had done some trick or kind of a manipulation in the beginning, where just by doing these two transformations, we were able to align all three of x, y, and z. Okay, what was that manipulation that we had done in the beginning? Somebody can remind me? Can you see my screen here? First, we will align the. You can read this line, right? What did we do here? Can somebody explain? Hello? You guys are connected, right? Nobody knows or nobody wants to answer? Asadullah, you want to answer? You want to try?
Yes, sir. We rotate the y and z axis in a plane of x so that after the rotation of x axis in beta, it will be coincident with the z axis.
Well, actually, I think you are on the right track, but I'm not sure exactly what you said. So I don't want to spend more time on this one. So what we did was we rotated the local coordinates. Usually we don't rotate the local coordinate system, but in this case, we rotated the local coordinate system about xm. Okay, m is local coordinate system, m is member. So we rotated the local coordinate system about xm in such a way so that my zm becomes horizontal. Okay, when it becomes horizontal, that basically means that it lies on xszs plane. It lies on this plane. Okay, and what that ensured was that when I do the subsequent rotation about the ys axis, in such a way so that my xm, when I do the rotation about y-s axis, my xs becomes x beta right under xm. My z goes and aligns with zs or zm. Okay, so that trick we had done so that my zm lies on the horizontal plane. Right, that was the trick we had done. And the tricky part here was that in spite of doing this transformation, wherein we rotated the local coordinate system, we did not have to do any transformation. And that we were able to do because, Haripriya, why did we not have to do any transformation?
Can you repeat the question?
Okay. My question is, if you read this first line, it says first we will align the zm axis so that it is on the horizontal plane. So zm axis is this one, right? 3 or 6. These are parallel to zm axis. So we rotated the local coordinate system in such a way that this zm axis is in a horizontal plane. But whenever we do a rotation of any coordinate system, we have to do a transformation of that one. Okay, whether it is local coordinate system or global coordinate system. But in this particular case, we said that we don't have to do anything. We don't have to do any transformation matrix. We don't need to employ any transformation matrix for this operation. What was the reason for that? Monish? Yeah, Monish. Gomati, Akshay? Yeah, let's move quickly. Gomati?
Yes, sir.
Yeah. No? Okay. Who can answer now? Shayan? Hari?
Sir,
Yeah, Shayan, can you answer? Harish?
Sir, maybe there is no coupling effect, sir, when we rotate and axis.
No, no. Ranjit? No? Okay. Nobody in the class, huh? Okay, that was the very basic. I spent a lot of time last time. You guys need to pay attention more in the class. If you are not able to follow, please ask. I'll repeat it again. This was a trust formulation, right? So this is not universally true, but for a trust member, you remember we had discussed that only the I values matter, and I are basically the moment of inertia, which are direction dependent. But the cross-section area is not direction dependent. Correct? So the only cross-section property that matters is the cross-section area. So when we rotate the member about its own longitudinal axis, its own x-axis, it does not change anything as far as the problem is concerned, right? Because it's a truss member. I can rotate the truss member about its own axis. What difference does it make, right? Because only the cross-section property that I'm going to use is its cross-section area. I cannot rotate about y-axis or z-axis, because then if I do that, that means I'm changing the coordinate values. But as long as I'm rotating about only the x-axis, as long as I'm rotating only about the local x-axis, it is not causing any trouble. I will not be able to do the same thing for a space frame, okay? But for a space truss, I can do that because it's just a truss member. Is that clear to everyone?
Yes, sir.
yes.
Okay.
Yes, sir.
Yeah. Now moving forward, last time I had given you a question to answer. The question was, when xs comes, or when I rotate the y-axis about, when I rotate the coordinate system about ys by an angle beta, my xs comes right under xn, and we call that x beta. Okay, after beta transformation. So this is the beta transformation, r beta transformation. So this beta rotation takes place, and my x beta is right below xn. Fine. What I had said was that at the same time, my zs will also rotate by beta, move by beta, and will align with zm. How do I know that these two things will happen at the same time? X beta will be right under xm, and at the same time, my zs will go and meet, zs will become z beta, which will be aligned perfectly with zm. Anybody was able to think of this question last time?
So,
Very
here
disappointing.
x and z are in horizontal plane.
Leo, repeat please.
X and z are horizontal plane. If we project xm, then it makes beta with the x-axis and beta with the z-axis.
Yes.
That
Yes.
means yes.
Yeah. Monish, you are saying something?
Sir, both are mutually perpendicular angles. So
Which
one
both?
axis is straight,
Which both?
like global and local. Member and
Global and local are not mutually perpendicular.
Excuse me, sir.
Yeah, who is this?
Sir, Leo, sir.
Leo, tell me.
So that global coordinates are mutually perpendicular, and the local, if we take the projection also, it will be already the xm is in the horizontal plane. We make it that way, but we take the projection also of the local, it will be also in the horizontal plane. So if the due to the perpendicular 90-degree thing, if we move the one in one that to that below that thing, means if we beta rotated in that part, here also it should be moving the same unit now. Like
Okay, maybe what I'll do is I'll give you one more class to think about it, the rest of the class. I think, Leo, you are on the right track. Everybody, please think about it. Please get me an answer in the next class, definitely. When we rotate it by beta, why is it that X comes right under XM and Z goes and aligns with ZM? Okay, I'm only targeting one thing at a time. Either you can say that I'm targeting ZS goes and aligns with ZM, or then why does XS directly comes under XM? Does not align with XM, but why does it come right under XM? Okay. Everybody in the class, please have this answer in the next class. I'll move forward now. So this was the space stress formulation. This was the stiffness matrix. This was the transformation matrix R. But also we discussed the possibility when the member was vertical. So if the member was vertical, we could have still gone ahead with these formulations of cos beta, sin gamma, cos gamma, and so on, right? But we don't like to use these betas and gammas because they are kind of cumbersome. So we write these transformation matrices in CXZ format because we have the coordinates already. So it is much easier to use these. But when we use these, we introduce these denominators, which are cos of which is CXZ, which is square root of cos x square and cos z square, right? CZ square, CX square. Yeah, Viren, please mute yourself. Guys, please mute yourself. Okay, so because there are denominator terms which become 0 in this particular way, so then we have to write a separate matrix for that. If we were following this kind of formulation, then there was no issue, but then it is kind of difficult always or visualize always to define the beta and gamma values. Okay, so if you are using this kind of a formulation where you are not using cos gamma, sin gamma, cos beta, sin beta values, but you are using this Cx, Cy, Cz, these are basically projections. If these values you are using, then you cannot use the same matrix for a vertical member because some of the terms will become will be divided by 0. In that case, you can skip one transformation. So basically, what we saw was that there were two transformations: beta transformation about y-axis and gamma transformation about the z-axis, right? So we don't have to do the beta transformation about y-axis. We only need to do gamma transformation about z-axis, and this is the resultant transformation matrix. We have discussed this problem before for plane frame problems, right? So I'm not going to elaborate too much on that one here. Okay. Similar thing, so by using all these steps, as I have explained before, you can solve this problem. The program is already given to you. The problem is small enough so that even you can try to solve it by hand. It won't be too complicated. Okay, some matrix multiplications you have to do, but for that you can take help from MATLAB, or even I think Excel also allows you to do matrix multiplication, so you can use Excel also. Fine. Moving forward, now we will go to space frame problems. Okay, so space frames. How are the space frames different from space truss? For a space truss, we had only 3 degrees of freedom at each joint. Agreed? So a space truss had only 3 degrees of freedom, 1, 2, and 3. But a space frame would have how many degrees of freedom at each joint?
6.
6.
Correct. Yes, there are 6 degrees of freedom. So the size of the matrix will be much larger. It's double the size. Okay. Fine. That's okay, that we can handle, right? As long as we are using a computer program, we can handle any size matrix. It doesn't matter. So this is the stiffness matrix. That is first challenge. That is easy to handle. The other issue is the transformation. Okay. So again, the local coordinate systems will be marked like this. So this is 1 in the direction of J to K. So that is 1, 2, 3. Again, we are following the right hand rule, right? Right hand rule. So 1 to 2 should be directing to 3. So once I turn my fingers from 1 to 2, my thumb is pointing towards 3. Okay, so which is okay, which is working fine. Likewise, 4, 5, 6, exactly the same, which are all rotational degrees of freedom. or moments degrees of freedom, moment vectors. Likewise, 7, 8, 9, 10, 11, 12. These are all local coordinate system or member coordinate system. Then you have structural coordinate systems which are aligned with the structural coordinates. So x, these are the x, y, and z coordinates, and then the parallelly you can draw the structural coordinate system at each joint. 1, 2, 3, 4, 5, 6, 1, 2, 7, 8, 9, 10, 11, 12. Okay. So now the challenge is to transform the stiffness matrix and force matrix, etc., from this coordinate system to this coordinate system. Yeah, we will see. So again, this time what will happen is that we don't have the freedom to rotate the member about its local axis. So you remember, for a space truss, we had done a rotation about the local coordinate system. So this was the local coordinate system. We had done a rotation like this, what is marked as alpha, about the local coordinates, about local x. We had done this rotation without any transformation matrix. That we cannot do this time. Okay, so we cannot do that transformation. So because of that rotation that we had done last time, we were able to accomplish two things at the same time. We were able to bring xs below xm, exactly below xm, in a single rotation. And at the same time, my zs had gone and met with zm. This time I won't be able to do that because I will not be able to bring my zm on the horizontal plane. Last time I was able to arbitrarily pick my zm direction in the horizontal plane so that zm was horizontal. This time I may not be able to do that. Fine. So we will have to still take care of that one. So let's look at a vector. This is the there is a vector which is known as in the local coordinate system. It is xm, ym, zm. Okay, so this is local coordinate system. Let me draw it also at the same time. xm, ym, zm. So these are the local coordinate system. The global coordinate system xs, ys, zs. Okay, and nothing is aligned with nothing. I'm assuming a very generic case, absolutely generic case. Okay. Now, since I cannot have the liberty of rotating anything about the local coordinate system without any transformation, we will not rotate, or we will not do any transformation about the local coordinate system. All we will do is we will always rotate the global coordinate system. Okay, that's what we have been doing mostly, except for one exception last time where we rotated something about the local x without any consequences. But this time, since there will be consequences, we will not do any local coordinate system rotations. We will only do the global coordinate system rotations. Okay, so we will go step by step. First, we will, our xm exists here, our xs exists here. Okay, xs is defining horizontal, right? So it's already in the horizontal. xs and zs together form the horizontal plane, and ys forms the vertical plane. So we will rotate our global or structural coordinate system about ys so that xs comes right under xm. That I can do, right? So wherever the xm is, if you can see this pen, this is, let's say, the member local x direction. So this is xm. Okay, and wherever my x is, so let's say this is xm and this is my xs. So all I'm saying is I'm bringing my xs right under xm, and xs was already horizontal. So I'm rotating the global coordinate system about the vertical axis. So my xs comes under xm. Okay, and that angle I will call beta. So that angle is basically beta. Fine, and I can do that. So I do that. My x beta is now under xm. When I say under, it means vertically under. Okay, and my zs goes somewhere to z beta, which is not automatically aligned with zm this time because my zm is not on the horizontal plane. Okay, so my zs goes to z beta. Fine. Now what I do is, I know that my x beta is already under xm, and I know what I need to do to align them. I just need to rotate about z in such a way so that x goes and aligns with x here. So x beta goes and aligns with xm here after a rotation called gamma. Okay. We do a rotation by gamma about z beta. So the new coordinate system that I get is after this rotation is z gamma, x gamma, and at the same time my y will also move from y, because earlier step when we did the beta, y did not move, but this time y will move to y gamma. Okay. So first rotation I did about ys, next rotation I did do about z beta, all right, and then I get z gamma. So I get x gamma, y gamma, sorry, y gamma, x gamma, and z gamma. Now, after this rotation, how many of the axes have aligned already with the xm or with the member coordinate system? How many of them have aligned?
X.
Only x has aligned, right? My z has not aligned. My z is still z gamma, but my zm is sitting here, which is not aligned with z gamma. My ym is sitting here. My y is not aligned with y gamma. But I have been trying single-mindedly to align my xs. So that's why I brought xs to x beta first. Then I took x beta to xm. Okay. So these two transformations allowed me to do that. Fine. So which are these two transformations? Beta and gamma in this order. Got it? So now what has happened? Now where am I? I have, let me put up some of these off. So I have aligned my xm and xs. Or in a way, I have rotated xs enough so that xs is aligned with xm. Now, basically, I'm talking about two different coordinate systems wherein one axis is common, right? So what does that mean? One axis is this one. This is xm, you can see, or you can say x gamma. X is common. Then what will be the y and z axis of the two? So let's say xm and x gamma. Let me draw m with a different color. Let's say member coordinate system that is also aligning with this one. Okay, so that is xm. That is in red. Okay, so probably it has these two axes, y and z. Okay, so this might be ym and this might be zm. Okay, and it has to follow the right hand rule. So x to y, you turn your fingers that way, and z is perpendicular to that direction. Fine. And then the other coordinate system is x gamma. Okay, and the corresponding y gamma and z gamma will be here. Agreed? Now, what do we know about these four values, these four vectors, ym, y gamma, zm, z gamma? They all of them lie in a single plane, right? Do you agree? And that plane is perpendicular to the x-axis. So there is, if you can draw kind of a plane, a circle sort of a thing you can imagine, all of them lie in that same plane. And that plane is perpendicular to this axis. Okay, you can imagine like an umbrella sort of a thing, a flat umbrella. So your x-axis is the shaft of the umbrella, and then you've got the umbrella sheet. So this plane is that umbrella sheet, and all these four vectors lie on that one. Okay, and both of them are perpendicular to. So this is perpendicular to this one, and this is perpendicular. Sorry, let me change the color. And this is perpendicular to this one, right? So zm is perpendicular to ym, and z gamma is perpendicular to y gamma. So what do we know from here is that which rotation is required to align all three of them?
About x-axis.
About x-axis, right? And that rotation we call alpha rotation. So I just need to rotate about x gamma, okay? Because I've been rotating about the global coordinate system. So from xs, I got x beta. From x beta, I got x gamma. And then again, I rotate about x gamma, wherein in that rotation, since I'm rotating about x, the x does not change its direction, but y and z do. So I rotate about x gamma, and in the process, my y goes and aligns with y gamma, and z goes, y goes and aligns with ym, Y gamma goes and aligns with Ym, and Z gamma goes and aligns with Zm. Okay, that's what I do. So that is called your alpha transformation. Okay, for that you will need this cos alpha, sin alpha values, sin alpha, cos alpha. What are these values basically? We will see through an example in a minute, but basically what will be happening often is that, if I may erase this, you would have a member which, and the local coordinate system, let's say this is your local coordinate system Ym and Zm. These are the local coordinate systems. So these are major and minor axes of the cross section. But the global coordinate system may not be aligned with that one. That angle will be alpha. Okay, and that is what this rotation is. So if once you rotate by alpha, okay, then all three axes will align. Until you rotate by alpha, only x will be aligned. That is, longitudinal axis will be aligned with the global longitudinal axis, global x-axis. But after this alpha transformation, all three axes will be aligned. Okay. So basically, which transformations we are doing? We are doing a transformation of beta, that is about y-axis, ys-axis. Then transformation by a gamma about z-axis, and transformation by alpha about x-axis. In this order. This is the first one, second one, and third one. Okay. Now, the values of cos beta and cos gamma and so on can be very easily found from from the coordinates, right? So we have done this one, this derivation. Likewise, this derivation can be done very easily from the coordinates. But the value of alpha cannot be found from the coordinates of the member alone. Okay, because that is basically, if you have a member and this is the major axis of this member, this is the longitudinal axis. The pen here is the longitudinal stylus. This stylus, you can see, this is the longitudinal axis, and the cross section has a major axis which is in this direction and the minor axis which is in this direction. Okay. Now, if this is aligned this way, I cannot get that information about the coordinates, right? So if I just know the coordinates of the member, the end coordinates of this one and this one, from that information, I cannot get the information about alpha. So this alpha information I have to get separately. So either the local coordinate systems have to be defined separately. So most of the softwares require you to define the local coordinate system. And as soon as you do that, then they can fetch that information. So usually you have to do that angle calculation. Okay. In this problem, basically I have to give you that alpha value and that you have to use. We will do an example to understand that. Okay. So once you get your R beta, R gamma, R alpha, you use them in this order 1, 2, and 3 to transform structural coordinate system into local coordinate system, right? So basically, again, a vector that was in a structural coordinate system, you do these 3 transformations in sequence to get them vector value in the member coordinate system. So AM will be equal to R alpha, R gamma, R beta. Okay, you have to remember the order. It is not alpha, beta, gamma, alpha, gamma, beta. That order is important. We multiply that with AS, that is structural coordinate system, and that's how you can change any vector in the structural coordinate system to the local coordinate system. Any questions? If you were not able to follow completely how this R alpha came about, anyway, the matrix here is pretty straightforward, right? For any transformation about x-axis, just like you had for other transformations, you would have one right where you are doing the transformation about which axis you are doing the transformation. Then the cos sine minus sine cos terms as it is. Okay, I would again also recommend you to read the textbook. I have referred the textbook here. I have given the name Weaver and Gere. Please read that textbook and you will get more explanation if you are interested. Or otherwise you can email me. I can give you I'll copy paste the material from the textbook. Okay. Again, that question of vertical members still remains unanswered because like before, the Y transformation cannot be done because the Y transformation has some terms in the denominator, beta transformation, rotation about Y. As soon as you do this transformation, you will bring in terms in the denominator which can become 0 for a vertical member. So either you use these matrices directly, but if you don't know the values of beta and gamma and you want to use the coordinates, then you have to use this matrix, but therein we have introduced this issue of zero values in the denominator, and for that you have to skip the transformation about y-axis or beta transformation. Okay, so you just go directly to the gamma transformation by rotating it about the z-axis, and this will be the transformation matrix, okay, for a vertical member. And the values of cy and values of cy are already given, whether when the member is vertically upward or vertically downward. Okay, that depends on what decides whether the member is vertically upward or downward. How do we know that member is vertically upward or downward? It's a member, right? It's not a vector. Hello? Prithvi?
Sir, if you are going from I to J, it has to be aligned to with y-axis, sir. Then we can say that it is vertically upward.
And otherwise?
Otherwise, it is vertically downward, sir. If we are going from I to J, if it is if it is not if it is in negative y direction, then it is
negative y direction. Correct. Yeah. So yeah. So if you know the answer, please answer. Right. Don't wait for me to call your name. Fine. So yeah, if the member is going in positive y direction, then it's upward. It's vertical still, but it is upward. So then that's why you would have cy is equal to +1. Otherwise, you will have cy is equal to -1. Okay, it's written right here. It is oriented in the direction of y plus y and minus y. And that is basically the definition is you have member I, which has joints j and k. So if j to k direction is parallel to plus ys, then it is upward. If it is the way you have numbered the members, it's up to you. If you number the members this way, then it is parallel to minus ys, then it is -1. Got it? Okay. Fine. So basically your R matrix, which is a multiplication of R alpha, R gamma, R beta, can be pre-multiplied already. So I have multiplied these three matrices, and this is the net matrix of transformation. And that is only for a vector of what size? It will transform a vector of what size? Here, if you see, this R can be used to transform a vector of what size? This R. Again.
12 by 12. Sir.
No, this R cannot. This RT can be.
This will be for 3 by 3.
Yeah. So only for a vector. So that is 3 component vector, not 3 by 3. That it cannot be used for a stiffness matrix. Okay. For a stiffness matrix, you have to do R transpose stiffness matrix R. Okay. This is only for a vector. So if you have a force vector or if you have a displacement vector of 3 components, you can use this. But in a member, we have 12 by like 6 on each side, right? So that is total 12 vectors we have to deal with. So if you have a force or displacement vector for a member, you have got 6 displacements here and 6 displacements here, right? You've got total 12 displacements. For 12 displacements, you have to use RT, which is given by this matrix, which is RRR in the diagonal values. Okay. So that basically summarizes the whole thing. So once you get your RT, you can also use RT transpose. So for transforming the stiffness matrix, you have to pre-multiply with RT transpose stiffness matrix RT. Okay, so this will give you stiffness matrix in SSI. So stiffness matrix in the structural coordinate system. This is the stiffness matrix in the member coordinate system, and you have to use this RT transpose. Okay. This is for the stiffness transformation. For a vector transformation, this is simply RT multiplied by A. Okay. A is basically a 12 component vector for ith member. That would have been enough in the structural coordinate. So if this is in the structural coordinate system, you will get A in the member coordinate system. Okay, fine. Any questions? Okay, so we will move forward with a quick example. So this is a space frame problem, right? So 1, 2, and 3 are the members, and some loads are given. Right now, you don't have to worry about the loads. We will just look at the transformation for one member, right? So I have solved in the lecture notes for one member, that is member 3, which is having a local coordinate system, which is given as x, y, and z here, and the structural coordinate system is given as x, y, and z here. Fine. So the structural coordinate system x, y, and z, which is given in capital X, Y, and z, these are universal for all three members, but every member has its own x, y, z given to you. So member 1 has its own x, y, z. Member 2 has its own x, y, z. So when x is given, that means this is joint J, this is joint K. X is this, that means this is joint J, this is joint K. When x is this, that means this is joint J and this is joint K. You are going from here to here. Okay, that is obvious. That is the very basic convention that we are using. So this is joint J, this is joint K. Fine. For this member, likewise for this member, this is joint J and this is joint K. Okay, so we will look at the transformation matrix required for each member one by one. So for the first member, you got x direction here. This is the global x, this is the local x. Then you got local y, you got global y. You got local z, you got global z. So what transformation is required for member 1?
No transformation is required.
No transformation is required, right? So in other words, your R beta, R gamma, and R alpha, they will all be unit. You got it right? They will all be unit for member 1. Or alpha will be equal to alpha will be equal to 0. So you get 1, 1, 1, and these terms will become 0. And these will become 1. Fine. So member 1 is no issues. Now look, let's take a look at member 2. For member 2, if you notice, the x is this one, local x is this one, but global x is in this direction. But it's a vertical member, right? You may notice that member 2 is a vertical member. When it's a vertical member, you may remember that we did not do the y transformation, or beta transformation was skipped. So we don't have to rotate about the y-axis. What we did was we rotated only about the z-axis. That was gamma transformation. Am I correct? Rotation about the z-axis was the gamma transformation. For a vertical member, we only have to do that. So let's think about how we will rotate about z-axis. No, but not about this z-axis. We have to rotate about the global z-axis. So how we will rotate about global z-axis, the global coordinate system, so that they align. So what rotation do we need to do? Vishal?
Yes, sir.
Yeah.
So I have to rotate global z 90-degree towards x, global x.
So I have to rotate the global coordinate system about the z-axis in such a way so that my global x becomes vertical.
Yes, sir.
Correct. So I have to rotate about z-axis by 90 degrees in the anti-clockwise direction.
Sir.
Right, looking into z-axis anti-clockwise. If you're looking
Yes,
out
sir.
of z-axis, then clockwise. But we always look into the axis. So we look into the axis that is in this direction. We look into this direction, and then anti-clockwise 90 degrees. Okay, when we do that, my global z remains here, but my global x comes here. So I'll call it x gamma, and my y becomes, instead of y being here, it comes here. So it becomes y gamma. Agreed? Now
Yes, sir.
it is, yeah, but it is still not aligned with my x, z, and y here, right? Now what has happened is that my x has aligned, my x gamma has aligned with x local, but my z local and y local are still not aligned. Now what do I need to do? My z global is here, my y global is here, my x global is here.
Now I have to rotate x in anti-clockwise direction again to 90 degree. So
Correct.
I'll
Very
rotate
good.
about x.
So yeah, so I will rotate about x, again looking into x in anti-clockwise direction. So when I do that, in that process, my z will come here. So I'll call it z alpha. This is alpha rotation, right? This is alpha transformation. And this y will come here. I'll call it y alpha. Okay. So z will be aligned with z alpha, y will be aligned with y alpha, and x will be aligned with my x gamma, or that is now x alpha after alpha rotation. Fine. So what was your earlier? There was no y rotation, of course. So that is done. What was your gamma value?
Gamma value is 90 degrees, sir.
Yeah. And what was your alpha value?
90 degree.
Okay. So for very good. So gamma value, you don't have to necessarily know. That way you can get from this matrix directly. For R vertical, this is already available to you. You can get input this value this matrix directly, but we don't have a value of alpha available to you. See, cy directly will give you. We'll see how you get the cy, cx, cz values. That is straightforward. But alpha value is not available. So alpha you have to calculate. So even though for the second member, apparently there was no issue, but still you could see that you have to rotate alpha by 90 degrees to align it perfectly, right? So alpha is 90 degrees. So that you have to keep in mind. Alpha turned out to be 90 degrees for the second member. Okay. I have not solved these. You just make a note of this for your future reference. Member 3, I have solved in this lecture notes. So we will see how to do that. For member 3, you can see that this is the local x, y, z coordinate system. Okay, this is following the right hand rule, and global x, y, z coordinate system is given here. So we will follow the steps as explained before. First, we rotate about which axis? About y axis, right? That's the first one. And we rotate in such a way, so we rotate the global coordinate system only about y axis until this x becomes horizontal. Now the issue here is that, sorry, x is already horizontal. X comes right below the local x, right? But in this case, what is happening is that local x is already horizontal. So in that process, in the y rotation, it will not come below x, it will be aligned with x directly. Okay. But anyway, we will follow that. So we will rotate about y axis, global axis, by an angle. By what angle? 90 degrees. Okay. In the clockwise direction. Okay. So we rotate by 90 degrees in the clockwise direction. My x will, this is beta. So my x will become x beta. My z will go here and will become z beta. Okay, and my y will become y beta right here. Okay, now x is aligned already, so I don't have to do the transformation about z. You remember? Because earlier when we were doing that transformation, we were having to do it because my x was not aligned with x yet. So I had to align x with x. That's why I was doing z transformation or gamma transformation. Now gamma transformation is not required, or in other words, gamma transformation will be an identity matrix. Fine. So we don't have to do that. Okay. So now x is already aligned. Once x is already aligned, now look at the global coordinate system. I've got x here, I've got z here, I've got y here. And local coordinate system is saying x is here, y is here, and z is here. So what transformation do I need to do to the global coordinate system so that it matches with the local coordinate system?
Alpha transformation, sir.
Alpha transformation. By what angle?
30 degrees
30 degrees.
anti-clockwise about
Exactly.
x-axis.
Yeah, so anti-clockwise 30 degrees about x-axis, global x-axis or beta x-axis, right? So this is alpha. Agreed? So if I do that transformation, my y will go rotate by 30 degrees this way, my z will rotate by 30 degrees this way, and then they will align with ym and zm. Okay, so that's what I am summarizing here. So first we rotate. I'm solving for the third member only. So this is the third member. You have got some local coordinate system. So these are the global coordinates. These are the local coordinates. Okay, so first we rotate the structural system by beta. As I had mentioned before, beta was 90 degrees. Beta is equal to 90 degrees about ys, and you get r beta transformation. And then gamma transformation was not required, as we had discussed. So r beta was cos 90 minus sin 90, sin 90, whatever the values are, and you get the values. Then gamma transformation is not required. So your gamma transformation, you can write it as an identity matrix, or you can simply skip that step because you are anyway going to multiply, so it will not have any effect. Then alpha transformation. So alpha is 30. So you put this matrix, and this is that matrix. You multiply the three, r alpha, r gamma, r beta, you get r matrix. You put r matrix together, you get rt matrix. Okay. This is if you know the angles. So I had to manually calculate or think about the angle values. Now this angle you have to anyway calculate, and you have to be careful about. So alpha angle you have to calculate, okay, because you cannot get alpha value directly from the coordinate system or the coordinates of the ends. But the r beta and r gamma values we can get directly from these matrices that we have developed. Okay, so look at this member. I'll go back again to this member. Okay, let me erase all of this. We are talking about member 3 only, right? So for member 3, what is the projection of this member length in the x direction? In other words, what is the difference? So let's say it has some coordinates, coordinate x1, y1, z1. Okay, this is JK. So xj, yj, zj. It has some coordinates here. And this also has some coordinates xk, yk, zk. Okay. What was cx value? You remember what was cx? So if the member length is L, this is the member, its length is L. So its projection, this member's projection in the x direction, global x direction, is called LCX. Agreed? So member's projection divided by member length is CX. Likewise, member's projection in the y direction divided by member length is CY. Member's projection in the z direction divided by member length is CZ. Follow it? So for this member, what is its projection in the x direction? 0. This member's projection, member length's projection in the x direction, or what is the difference between this x and this x? Basically, what will be the projection? The projection will be this distance minus this value. So xz minus xk is how much?
0.
0 divided by L. 0. Okay. What is cy?
Zero.
What will be cy? 0.
0, 0, sir.
What will be cz? Its projection in the z direction?
20 feet, sir.
Yeah. It will be 20 divided by member length, right? So how much is it? 1. Agreed? Divided by length also. So I got Cx, Cz, Cy value. So Cz is 1, Cy is 0, Cx is 0. And then I can get Cxz. Cxz is how much? How much is that? Agreed? So I got Cxz, Cx, and I substitute those values. I get R beta. Likewise, I can get R gamma. Okay. So as you may remember, before we had said R gamma will turn out to be an identity matrix. That's what it turns out to be. Fine. So even if you don't do that mental calculation of calculating exactly what is the angle, you can still get that directly. Okay, using the program. So in the program, you just have to give the coordinates. From that coordinates, it will calculate Cx, Cy, Cz, and it will calculate Cxz, and it will calculate the R beta value. Now look at your R beta value here. Got 0, 0, 1, 0, 1, 0, minus 1, 0, 0. You got same thing, 0, 0, 1, 0, 1, 0, minus 1, 0, 0. Okay, but we are using two different methods. Earlier we were using the angle. Here we are using the projections. Fine. And then alpha, as we had discussed before, alpha will be 30 degrees. But you have to do that mental calculation to calculate the alpha value. And that's what you will get, alpha, R alpha. And then you multiply the 3, you will get R. And then you put them in this sequence, you will get RT. Got it? Fine. Any questions about the space frame? So for the space frames, in addition to your stiffness matrices, you also need to know the transformation matrix. And this R alpha transformation is something that you have to do some mental calculations for in order to get the exact alpha value. Because apparently, if you remember, the second member did not have any awkward angles, right? It was all aligned perfectly fine with X, Y, Z, only thing. But still you saw that alpha was equal to 90 degrees for this member. Okay. So until you do the first two transformations, you would not know what alpha value will be required. Got it? Okay. Now there are two other topics that are of importance for you to get a fully functional program going on. One problem is when we deal with it, so far the way this derivation was done, this entire formulation was done, either a structure was a truss structure or it was a frame structure. So when the structure was a frame structure, there were no hinges in between. Okay. So the degrees of freedom were perfectly overlapping. If it was a truss structure, then there were no fixed joints. All the joints were all pinned, right? So there was no in between. But it may happen often is that you have mostly a frame structure, but a few hinges in between. Or you may have mostly a truss structure, but one beam present. Okay. So when you have that kind of situation, then you should be able to handle it independently, and then you have to apply some thought to it. So here I'm giving you an example, and through an example, I'll show you how to handle this kind of a situation. You have to create extra degrees of freedom corresponding to the hinge. So this is basically a frame, a beam rather, okay, a continuous beam or a fixed beam. But what I've done is I have put a hinge in between, and I'm applying a load right at that hinge. So how to solve this kind of a problem? You know the formulation for a frame or a beam, and you could simply use that formulation for the beam. If I had given you a simple node here without a hinge, you would have divided this beam into two parts, part 1, part 2, and simply analyze that beam just like following the process before. Right? We have solved beam problems in this in these lecture notes, but this is a different type of a problem slightly because of the hinge. I've got an issue here. So I have to, as you might have done in the past, you have to add some degrees of freedom here. So which are the two members that I have to take? I have to take one member here, one member here. This is member 1, which is made of degrees of freedom 1, 2, 3, 4, right? One is the vertical movement because it's a beam. It is allowed to move. It's a plane beam, okay? But it could be a space frame also. That extension you have to do. So this is a plane beam. So it has only 2 degrees of freedom at each joint. 1, 2, 3, 4. Perfectly fine. The second beam, again, 3, 4, 5, 6. Right? But it is not 3, 4, 5, 6. Why is it not 3, 4, 5, 6? Why I have marked it as 3, 5, 6, 7? So far, the way I have been doing it, this is the common joint between the two members. So this will have degrees of freedom 1, 2, 3, 4, and this will have degrees of freedom 3, 4, which are same as this one, and 6, 7. Agreed? But I'm not doing that here. I'm changing it slightly.
Because the rotation will be different for the left part and then for the right.
Exactly. So the rotation here will not be same as rotation here, but vertical movement here will be same as on this side will be same as vertical movement here. So 3 and 3 are common, but 4 and 5 are not common. Okay, that's why I'm giving them different numbers. And I can very easily develop the stiffness matrix for this member. I already know the formulation, and I can develop the stiffness matrix for this member. Okay, right. So as long as you do that, you make sure that you don't put this 4 and 4 common in the program and put a separate degree of freedom for that one. And you can ask that information from the user to input any hinges and about which axis the hinge is, and from that you can extrapolate that information. So this is the stiffness matrix for this member. Same stiffness matrix exists for the other member, right? This is just a stiffness matrix for a plane beam. Agreed? Now we can simply assemble it. While assembling, we have to remember that we have to, the members of the terms corresponding to 5 do not add with the terms corresponding to 4 degree of freedom, because these are independent degrees of freedom, 4 and 5, right? So 1, 2, 3, 4 will come here directly, but 3, 5, 6, 7, 3 terms will go to 3 terms, they will be added. 3 from here will add to 3 from here, but then nothing adds to 4. So the blue colored boxes are corresponding to second member. So the 3 adds to this one, but then you put terms corresponding to 5, 6, and 7 separately. Agreed? Then this is your global stiffness matrix. What is the size of your stiffness matrix global? 7 by 7, right? If this hinge were not here, you would have had 1, 2, 3, 4, 5, 6, total 6 by 6 matrix. But now your global stiffness matrix is 7 by 7, out of which how many degrees of freedom are free? Out of 7, how many are 3 degrees of freedom?
So three degrees are free.
Which ones?
4, 5, and 3.
Yeah, 3, 4, and 5. So basically now the next step is to separate the free degrees of freedom. So SFF, I'll take the terms corresponding to 3, 4, and 5, right? So which were the terms corresponding to 3, 4, and 5? This is 3, 3, this is 3, 4, this is 3, 5. Likewise, 4, 3, 4, 4, 4, 5, 5, 3, 5, 4, 5, 5. So this part I'll take out. That I write as the SFF matrix. I knew the load value at T, which was again the 3 degrees of freedom. So these are the loads acting at the 3 free degrees of freedom, which is minus P 0, 0, the SFF multiplied by D3. And I can solve for this 3 degree of 3 component vector. Correct? So if you give me the values of I, E, L, and P, and etc., I can substitute all those values here and I can solve for D. Okay, and this is the value I get. So the deformation, vertical downward movement is 0.416, whatever the units are, millimeters. Okay, so this is how you solve it, and this is how you can implement it in your program also. You have to seek the information from the user. There is a user input part, right, in the program. There you need to ask the user to input if there are any hinges. For truss, it is not applicable, but for whenever you have a beam, then you have to ask for that information. Got it? So you have to apply some mind there to solve such kind of problems. Then the last topic for today is the stability. I have been saying from the very first lecture that the stability of the system is a bit of a problem which cannot be understood directly by doing that calculation of indeterminacy. It may not always be universally true, but there is another method which is known as the stiffness matrix determinate method. Okay, so you can calculate the determinate of the stiffness matrix, and if it turns out to be non-positive, then it is an unstable problem. So for an unstable structure, your SFF will turn out to be 0. It will not be positive. Okay, or if it is very, very small positive value, then we often call that an ill-imposed problem. So if you visualize this picture, yeah, this is kind of a truss, right? It has got 2 supports. both of them are pin supports, they don't move. You got a hinge here, you got two truss members. Now imagine that you change this angle slightly, okay, and we can play with this angle. So let's say the members dimensions are such that this member is already almost horizontal. So when it is perfectly horizontal, this problem is, what kind of a problem is it? So our system, it is
Indeterminate.
Unstable.
indeterminate. It's an indeterminate problem if you do that calculation, but we are talking about something different. See, it is indeterminate here, I agree. No, it's not an indeterminate problem. Why is it an indeterminate problem? No, it's not an indeterminate problem. In fact, if you release anything here, it will become
Telling you the second thing.
yeah,
sir.
yeah. So it's a determinate problem. See, if any member is slightly longer, you can accommodate that easily here by changing the angle slightly. So it's a determinate problem, but it's here it is stable and here it is unstable. So for example, here if I apply a load, this will resist that load by compression in the two members. But if I apply any load here, no matter how much force these members apply, their vertical component will always be zero, right? So until it deforms quite significantly, and that is what its mechanism is. So until it turns into a mechanism, it will not be able to resist any load. Okay, agreed? So until it deforms quite significantly, it cannot resist the load. That's why it is an unstable problem. Now there can be situations where this angle is very small. So right now this is very large angle. If I may draw this angle. So right now, in this case, this angle is 0. If I draw the extension of this one, tangent, and this angle is 0. Here in this case, this angle is pretty large. Okay. If I put this theta, let's say 1 degrees or 0.5 degrees or something like that, and then you solve for this SFF determinate, you will see that it turns out to be marginally positive, and that will be a sign of an ill-imposed problem. Okay. Anyway, so we will see what it means here. So I'll not be able to give you a theoretical derivation of why determinate of SFF being 0 means that it is unstable. You can get a lot of explanations on the internet. I'm sure you can find time to explore that idea. All I'm telling you here is that if the determinate of SFF, it is not entire S, because entire S does not account for the boundary conditions. It is only after accounting for the boundary conditions, you get the SFF matrix, which is free degrees of freedom, right? So the stability depends quite significantly on the boundary conditions. So of course you have to have SFF. So the determinate of SFF, if it is 0, then it is an unstable problem. If it is positive, it's a stable problem. So this I'm doing through an example here basically. So if it is a truss member, plain truss member, you remember the stiffness matrix in the global coordinate system we had developed already, right? So in the local coordinate system, the stiffness matrix was 1 0 0 0 0 0 0 0, I think. Oh, maybe I'm making a mistake here. 1 minus 1 was there. Let me go to plain truss. Another for minus 1. Then plain truss, right? So the stiffness matrix was this one: 1 0 minus 1 0 0 0 0 0 minus 1 1. Okay, and the transformation matrix RT already, which is for the 4x4 vector, 4 size vector, was this one. Okay, and then we had derived it for the stiffness matrix in the global coordinate system. So we had done this multiplication with RT on both sides of SM to get SSI, and this is what we had got: AE by L, CX square, CX, CY, etc. So we can use that one directly here. This is the stiffness matrix for each member in the global coordinate system. Okay, wherein CX and CY we can calculate from the projections. Okay, so its projection in the X direction, its projection in the Y direction, that will govern what is the CX and CY value. So for this particular problem, let's say this one, what is the CX value for each member? its projection is only in the x direction, right? It's extending only in the x direction. So its projection on the x-axis is 1. Its projection on the y-axis is 0. So this is your stiffness matrix for each member. You add the 2 because you got 1 and 2 degrees of freedom here, 3 and 4 degrees of freedom here, 5 and 6 degrees of freedom here. So 1, 2, 3, 4. This was the stiffness matrix for the first member. This is the stiffness matrix for the second member. So it was supposed to be 1 here from both sides. So that's why it becomes 2. Okay. The rest of it is as it is. Okay. And what is the SFF size here? Which degrees of freedom come in the SFF? Which are the free degrees of freedom here?
3, 4.
3 and 4, correct. Because this is a truss, right? So actual movement is also allowed. 3 and 4. So that means this is 1, 2, 3, 4, 5, 6. That means this one. So we will take this part of the stiffness matrix. That will be my SFF matrix. We take this SFF, which is AE by L 2000. And if you take the determinant of this one, what do you get?
0.
0, right? So since the determinant of this one is 0, you will not have. So the system is an unstable system. That's how you can show. Okay. Even if a system is locally unstable, this determinant will turn out to be 0. Okay. So that is a short way of knowing whether there is any instability or instability in the system. Fine. So you need to do this check also for each of your problems. So there are 5-6 problems given to you in the project. You need to first check, develop the stiffness matrix, then check whether the stiffness matrix, after you take out the SFF part, check whether that is, the determinant of that is 0 or not. If it is not 0, then only you solve the rest of the problem. Otherwise, just report that it is an unstable problem. Fine. Any questions? With this, we are concluding the matrix method for stiffness stiffness method using matrices, and we will go on with the non-linear problems in the next class.